In this video, we will introduce the concept of implicit differentiation. And to do so, we're going to look at this motivating example. We would like to find the derivative dy dx if x squared plus y squared equals 25. Now, the idea behind implicit differentiation is that in this example, no matter how hard we try, we're not going to be able to write down y explicitly as a function of x. And the reason is, note that if you solve for the y, you'll have y squared equals 25 minus x squared, so that y is equal to plus or minus the square root of 25 minus x squared. So for every input x, you have two corresponding outputs. This is not a function. So instead, what we are going to do to differentiate is introduce the concept of implicit differentiation. So to differentiate implicitly, what we will do is take the derivative of both sides of this expression with respect to x. So if x squared plus y squared is equal to 25, then their derivatives with respect to x are going to be the same. So on the right-hand side, we have the derivative of a constant, which is 0. And on the left-hand side, we have the derivative of a sum. So we can think of this as being the derivative of x squared plus the derivative with respect to x of y squared. And a very important observation to make is that the derivative of x with respect to x squared is an explicit derivative. By the power rule, that's 2x. However, to differentiate y squared, this is what we are going to call an implicit derivative. Now, how we could write this is y is really something that depends upon x. And I know that because we're trying to find its derivative with respect to x. So when we write y, we could really think of y as being the function y of x. And when we see it in this form, we notice an inside function y of x and an outside function which squares. So in order to differentiate this, we need to use the chain rule. So 2 times y of x, the new power would be 1, and we multiply by the derivative of that inside function. So here we would note that the derivative of y squared, how you differentiate this from a very intuitive perspective is because it's a derivative of y with respect to x, we differentiate that y squared exactly as we would like to by the power rule, 2y, and then by the chain rule, we multiply by dy dx. And this is what we think of as being an implicit derivative. So you differentiate exactly as you would like to, the 2y, and multiply by dy dx. Now where does that dy dx come from? It's simply the chain rule, as we've used above here, in disguise. So the derivative with respect to x of y squared is 2y dy dx. So now that we have differentiated both sides with respect to x, we see the thing that we would like to solve for, dy dx. So let's go ahead and algebraically isolate it. We can subtract 2x from both sides, and then we can go ahead and divide both sides by 2y. So when we do so, the 2's cancel, right, because we have that 2 on both sides, and we have minus x over y. And this is our first example of the process known as implicit differentiation. Now, from a procedural standpoint, let me just note that when we are solving for dy dx via implicit differentiation, we follow the procedure we introduced in the previous example. Differentiate both sides with respect to x. Once we do so, you're going to have some dy dx terms present. And what we will need to do is algebraically isolate the dy dx. So collect all the dy dx terms on one side of the equation, say the left, move all of the other terms to the right-hand side, and then algebraically isolate, i.e. solve for, the dy dx. In terms of implicit differentiation, let me just note of a few circumstances where we have to be careful. Occasionally we might see something like, say, the derivative with respect to x of a term like xy. And when we see this, we remember that y, we're really thinking of it as a function that depends upon x. So we have one function of x, the x, times a second. So what we are going to have to use is the product rule. So we would take the derivative of the first times the second plus the first times the derivative of the second. So the derivative of x is 1 times y plus x, and the derivative of y with respect to x, implicitly we differentiate the y exactly as we would like to, a 1, and then we multiply by dy dx. So y plus x dy dx. So let's look at another example and see this process at work. Let's use implicit differentiation to find dy dx for the quantity given here. So the first thing that we need to do to implicitly differentiate is to differentiate both sides with respect to x. On the right-hand side, when we differentiate with respect to x, there are no y's present, so it's just an explicit derivative. So in this case, 3x squared plus the derivative of minus 1, which is 0. On the left-hand side, in the first term, we have one function, 4x squared, multiplied by another function, y. So to differentiate that first term, we must use the product rule. So we would get the derivative of the first, so the derivative of 4x squared is going to be 8x times the second function, which is y, plus 4x squared, the first, times the derivative of the second. And with respect to x, the derivative of y is dy dx. And then we subtract away the derivative of 3y with respect to x. So that will be 3, and this is an implicit derivative, dy dx. So we now note the thing that we would like to solve for, the dy dx. There are two of them on the left. So what we'll do is group those two terms together. You have 4x squared of them, and then minus 3 more. On the right, you have a 3x squared, and we'll go ahead and move the 8xy over to the right-hand side. So minus 8xy. And now we algebraically isolate dy dx, which is the quantity we wish to solve for. We have 3x squared minus 8xy on the right, and we are dividing this by 4x squared minus 3. So just to note those big picture kind of procedural steps, we differentiate both sides with respect to x. When we do so, there's going to be some number of these dy dx terms. Leave those on the left, move the other terms to the right, and isolate to solve for dy dx.